So thank you so much for coming. My name is Jack Porter. I'm the Unreal Engine 4 mobile team lead. And these days, a lot of my time is spent working on Fortnite. And today I'm going to describe some of the technical aspects of how we work as a team when we develop Fortnite. And hopefully some of this information can be applicable to some of your team's games. So we're going to talk about how we work as a team, and exactly how you work as a team really depends on the kind of game you're making. If you're making a game where you know what the goal is, or a game where you're iterating to try and come up with a fun game mechanic, what kind of influence you have in terms of what everybody has brought to the team, their experience shipping other games, and whether this applies especially to Fortnite, whether or not you're making a boxed game or a continuous online product where the game has to evolve and you have to be able to keep up with that process. And so I'm going to cover three main areas. First of all, how we distribute the editor to all of our content creators as we iterate on the game design. What our branching strategy is for source and content as we have an ongoing live game, and also some iteration, or some ways we iterate on both code and content. So first of all, how we distribute the editor. And this is a process we've used for a very long time at Epic. Going back before Gears of War, we used this kind of process where we had the build machine. Okay, so I should describe the problem here. And the problem is we want to iterate on improving the editor and tools and making game design specific features in the tools. And then we need to distribute these tools to the content creators so they can make the game using the latest version of the tools. And so our process would typically be, we'd have the build machine update a version number, and then it would compile the build and submit the binaries back to Perforce, our source control system. And then we'd give it to our QA department, where they would do what we call smoke testing. So they would basically check that we haven't broken anything major. You could still edit the game, and you could still load content, and there weren't any major issues. And then after QA approved a particular build, we would label it in the source control into Perforce, and then our artists would sync that build, and they would have a version of Unreal Editor that they could use and open content. Now, updating the version number at the top is not just a version number here. This is the version that's going to control Unreal Engine's property serialization. And if you know anything about Unreal Engine serialization, you'll know that it's pretty robust in that you can add some new properties to an object or an asset, or you could remove, and if you were to load an old asset that didn't have those properties, that asset would instantly inherit the default value. And similarly, if you removed some properties from an asset you didn't need anymore, the old data would just be skipped over the next time it gets loaded after the property's been removed. And this works because the editor can be sure about the version number of the asset that it's loading. And so if you have a very new asset saved with the latest version of Unreal Engine, and then you try to load that in an older version of Unreal Engine, we bring up a message to say the asset is much newer than the editor. And the reason we do that is that any properties that have been added in that new version of Unreal Engine would otherwise be skipped over and be lost. So we have to do this to avoid data loss. And so we have this cycle where every day the build machine is building a new version of Unreal Engine or the editor, and then test team is testing it. They quickly find bugs. They go through our process. The programmer fixes it. We make a new build. And so this cycle is very slow. And we were finding with lots of game designers adding new features, typically we'd have at most 1 or 2 good builds per day. And this really killed any kind of collaboration we're getting between game programmers and the content creators. There were other problems with having all the binary files in our source control. And that was, firstly, if a programmer downloads the binaries but doesn't compile them, they might get a Windows error popping up saying there's a DLL mismatch. Or perhaps, if they're unlucky, perhaps everything loads correctly, but there's a slight difference in the memory layouts and some content or memory gets corrupted and you get random crashes. So with this process, people were feeling, that the build process wasn't reliable, and that if they saw a crash in the editor, it was easy to explain that it was the cause of, a sync mismatch between the binary and the source code. And the second problem with this is that you cannot iterate on code and content together. And what this means is that a programmer who's downloaded their own version from source control and built their own binaries, if they were to edit some content and submit it, there's no way that version number can match any version number that artists would be using. And so our solution, what we do in that case is we submit the content without any version number at all, which means there's a possibility that data could be lost if it's being loaded by a content creator using an older version of the editor. And so at about this time, we're having this problem for Fortnite as we're scaling up this game using this process we've been using for many years. A small team were making a simple game called Battle Breakers, and there were just 8 people sitting in a room, programmers and designers and artists all in the same room, iterating and working on their game together. And they didn't like this process of having QA test the builds and approve them. They wanted a much quicker iteration cycle. And so their solution was simply to pretend that their content creators were also programmers. And so their content creators would download a version from source control, and they would load up Visual Studio, and they'd press compile, and at the end they'd have a binary, and they would edit their content. And as they're iterating on features with the game designers who are making systems and tools, there was really close collaboration between them. If they had problems, they could just turn around and communicate and say, hey, there's a problem with my build, what's going on? And the problems could be quickly solved. But not only that, we found that this kind of iteration allowed the game design to really flow much more freely than we were seeing in Fortnite. And so our idea was, why don't we try and make this work with Fortnite, see if we can scale it to Fortnite. And when we thought about this, we thought, that's going to be great, but are we going to sacrifice stability? Are we going to have corrupted assets all the time? Are the compile times going to be so terrible that we won't want to use this process? And so we looked at the different things that people are changing every day. And typically, the core editor workflows, such as opening a level and modifying some assets, moving actors around, placing objects, those workflows are not touched by programmers very much. So we felt pretty good that they would be pretty stable and there wouldn't be any major issues there. On the design side, the game designers are quickly, they're making new blueprint classes that can be used by the gameplay and the level designers. And they are making tools that are being used by the content creators. And so we're worried that there would be some stability problems there. But at the same time, we felt that the improved productivity in terms of iterating on the game design was really worth it. And finally, the memory and asset corruption bugs that we were seeing previously, we had a look at some of the cases we'd seen those kind of crashes before in the past, or those kind of bugs in the past. And it turned out most of the time, even though we had this very heavy QA process for our builds, they were not catching these kind of very subtle corruption anyway. Typically, they were limited to a single class or a single type of asset that didn't get caught anyway, and we still had the problem. We still saw the problem in the wild. We also we thought if we were to do this, we would have a lot more versions of the editor because anybody could build the editor against any version of the source code. So we had to be very confident that our versioning system would be reliable. And finally, there was the concern about not being in the same room as the engineers and the artists are not in the same room, so they couldn't easily discuss problems that did occur because of this workflow. But we decided to go ahead, and we had our QA, we had our IT department install Visual Studio Express for all of our artists, and then we developed a tool that would allow us a single-click workflow for our artists to be able to iterate on this using this process. And so this was our first tool. It was called Unreal Game Sync. And it's just a list of change lists that a designer can double-click. When the designer double-clicks the change list, it compiles it. And if it succeeded, we would send a little message to a database, and then that database would be used to put a green light next to that particular build, which indicates somebody was able to use this build successfully. And if the compile failed, we would leave a red dot next to it. But also, if an artist compiled and were able to load up the editor and found some functionality they needed was not operating correctly, they could right-click and they could leave a message indicating this build, the version of the editor is bad here, and here's an explanation of the problem. And then engineers could leave comments also saying, oh, we're investigating this issue, etc. So it was a big experiment with, at the time we were probably 50 content creators. We weren't a small team, and it would require a change in our culture, but we gave it a go, and we regarded it as a win for Fortnite. We were able to get back into this rapid iteration cycle of iterating on the gameplay. So after 4 years, it's still basically the same, but we've polished it a little bit and we've added some more features. We've added some tabs along the top so you can sync to multiple streams. We've added a status bar at the top with some links to loading up Perforce or loading up Visual Studio or launching the editor. But the new, the main addition is the central green area, which is the results from our automation system. So because we have a CIS system constantly building and testing various parts of our pipeline, cooking content or compiling for different platforms, we can highlight the individual change lists with whether a particular automation test has succeeded or failed. So it's very quick for an artist to come in, and if they're looking for a new version with a new feature they need, they can just find one with lots of green next to it, double-click it, and be pretty confident nothing's going to break. Our automation system sends these messages back to Unreal Game Sync with this little standalone application, which you can use to send any kind of message you like from any of your backend processes. And you can say whether something was a success or a failure. You can provide links, etc., as well as an API for that to interact with Unreal Game Sync. And this allows us to show desktop notifications. So if I have been editing some Fortnite editor code and I submit my code, I might come back 10 minutes later and find that the CIS or some automation test is failing for my build, and I'll have a little Windows desktop notification telling me I need to address something. And we found for Fortnite, we looked at what we could kind of do for a CIS system. And as you know, there are many, many different ways you can compile Unreal Engine. And this is what we found works best for us, using a single computer in our build farm for Fortnite CIS. And that is, we do an incremental editor build, so any source code changes are quick to compile. But we disable the source code unity feature, which allows us to catch missing include files, those kind of things. And we also run an editor session that opens up any brand new submitted content. And the point here is that when artists submit, maybe they're submitting a material and a bunch of textures and a mesh that goes all together, if they neglect to submit maybe the texture, but submit everything else quickly, this CIS job will very quickly identify that situation and inform the artist using the Unreal Game Sync notifications. We also check that our login flow continues to work, so that nobody's broken the ability to launch a game client, launch a server, be able to log into the server successfully and enter the game. Just by testing this, we can quickly stop problems that would otherwise prevent many people from working at once. So as I said, all of this is done on a single computer, which is a pretty good investment for the reliability that's added to our build process. And we added one second machine to our build farm, and it does a similar thing as the first step, but compiling binaries for each of our target platforms. So for PlayStation 4, Xbox One, Switch, PC, Android, and iOS. And using these two computers, we can very quickly detect a whole bunch of very common problems that it would otherwise be blocking users from developing. At the same time as we were developing Fortnite, we also had another game under development called Paragon that had a very, very heavy art pipeline. And we had a lot more artists than we had engineers on this project. And they wanted the distributed binaries pipeline. They didn't want to compile the source code themselves, but they saw the advantages that Unreal Game Sync was giving us to be able to collaborate and find builds and identify problems quickly. But we didn't want to put the binary files into Perforce like we'd done previously because of the programmer versioning issue that I described before. So instead, our build server generates a zip file, and we put that zip of all the binaries into a separate branch. And then we put the change list number as the zip file name, so they can be matched together with the source change list. So even though they're not compiling binaries themselves anymore, everyone in Epic is still using the same user interface. They're using Unreal Game Sync to get their builds, but in the case of Paragon, the builds that did not have matching binaries are grayed out and cannot be selected. And so while we are developing Unreal Game Sync and using this daily, we decided we were going to add a bunch of features that improved the usability of Perforce. So when we moved to streams from the original branch system of Perforce using the fast stream switching, we became frustrated that we lost this ability to filter out various things from our workspace. And an example might be you might want to filter out your the binaries for platforms you don't care about. So you might be a user who doesn't have an Xbox and a PlayStation. You don't want to get anything related to Xbox or PlayStation to save your disk space. And also maybe you're somebody working at home remotely and you don't want to sync any cinematic movies, etc. So we added a filter to Unreal Game Sync to allow you to choose, using some friendly checkboxes, what particular platforms and what particular classes of content you wanted to exclude. We also added the ability to clean a workspace, and this just resets an artist's machine back to a kind of pristine state, restoring missing data from the server and files that the user's modified without checking out. And this only looks at whether files are writable or whether they exist on disk or not. So it's actually really quick. We can do a clean in about 10 to 20 seconds on most computers. This also has the advantage of knowing where all of the Unreal Engine intermediate files are. If you know anything about Unreal Engine's plugin system, you'll know that intermediate files can be distributed in a number of folders, and this solves that problem. Now, because we've already got our programmers and our artists using this tool, we thought we'd put QA on it as well. And our QA department, when they are trying to work out when a bug occurred, can multi-select a couple of change lists, and then they can binary search between them to find the cause of particular crashes or a particular issue that they're seeing. And there's a sync next option you can press, which will divide the range in half and take you to the next change list. Finally, there's a lot of customization we've done. First of all, we can customize the logo, but also the background. And we use the background for signifying the state of a particular branch. So in this case, it's red, which indicates this is a release branch, and this branch is already locked down, and therefore no submissions should be happening in this branch. It's a good indicator for the level designers and artists so that they know where they should be working. Users can configure automatic syncs at certain times of the day. So I've got mine set up to sync every morning at 6 a.m. And I come into the office and the sync is complete and my workspace is updated and I have a binary version of the editor ready to go. We can also update with a bunch of links, such as links to outstanding bugs for this release, or we can provide some text, which is the information we want to send to the team, such as important dates, such as when the next release will be happening. And all of this is configurable using some config files. So if you guys use Unreal Game Sync, there's no special Epic internal version. There's only the version we have shared with you guys. The source code for Unreal Game Sync is on Perforce and on GitHub, and it's not synchronized to any binary release, so I recommend you get the latest version. There's a lot of docs on docs.unrealengine.com explaining how to set it up and how to use it. And as I said, it's compatible with any engine version. The second topic I'm going to talk about is how we control our branching model for Fortnite. And this is the source control branching model. And so this is the model we started with Unreal Engine development. We've had this for a long time. And when we started using streams, we followed the recommended practices that Perforce had put out, which was to put the most stable streams at the top and then have those changes filter down to the least stable streams at the bottom. And so those release branches would typically not have any changes at all unless we're making a hotfix. And any changes we would make would trickle down to main and then to all of the dev streams. But if we're in a development stream, like in Dev Editor, wanting to push some new code changes upstream, we would have a very heavy QA process where they would verify that nothing has been broken before we were allowed to copy into the main stream and then make a new release stream. This works really well for source code because source code can be merged. If two different streams are modifying the same file, then you just take this change, and both of those lines are merged together. But this system works very bad, is very, very bad for content because you cannot merge content assets together. If two users both happen to work on the same animation file in two different streams, when you merge to main, one of them is going to miss out and his work will be thrown away. So we've moved to this model for Fortnite initially. And the idea here was just to have 3 streams, going to reduce the number of places where these conflicts can occur. And the 3 streams were the main stream, where we are editing or doing most of our future-looking content development. We have the next release, which is a place where we're stabilizing a release just before we give it to the public. And we have the live version, which is what's out there right now. And this is okay, but it caused a problem when there was a delay. So if we had to delay a release because we had some issues with it, people would be confused as to where they should be working. They thought, oh, we're going to push the release live on this day, and so they're working in main instead of release next. But in fact, they should have been working in release next. And the second problem was that we made the live build from the release next branch before copying it into the release live stream. So the very first time we were testing all of our automation systems on the live stream was when we're actually moving that version to be live. So that made a point where we could have a lot of possibility for things to go wrong with our automation system. So we moved to this model. This has been working very well for us for about 1.5 years now. The idea here is to have one dead-end branch for each release version. And the streams are named so that artists always understand where they should be working because they know what release a particular feature or content that they're working on should be targeting. And we release new versions of Fortnite every 2 weeks, but we want to stabilize for a number of weeks, including 3 weeks or more usually. And so this gives us the ability to be stabilizing release 8.20 while release 8.0 is still out in the wild. When we want to make it, or if an artist needs to make a change to an asset that is in the live version, it makes sense that we also want that change to propagate downwards to the 8.10 version and the 8.20 version and all the way into the main version, so it will be in future releases of Fortnite. but we don't typically push anything upstream at all. And this works well. We can scale the number of branches we need depending on how many versions we're testing in flight and how many versions we're developing for. So after version 8, once we've started to work on version 8.30, we would put a new stream in between the 8.20 and the main stream. So we modify this stream layout every time we add a new version. And our artists use the Perforce fast stream switching system to change their workspace to point to a different release. And in fact, we've set up Unreal Game Sync so that Unreal Game Sync can automatically or can automatically switch between streams for our developers and artists. So, as I said before, we would want to merge the changes made in, for example, 8.10 down to 8.20 and down to main. But we still had problems with conflicts because we would have one poor engineer who would have to do the merge at the end of each day. He would be merging each version into the next version. And there would still be conflicts to deal with. For example, an artist had modified an asset in release 8.10, and somebody else had modified the same asset in release 8.20. So instead of having a single merge at the end of the day, we added this tool, which we also made available to you guys, called RoboMerge. And RoboMerge takes every individual change that we submit to our source control and propagates it down to the next stream automatically. And that way the conflict becomes, or the resolution of the conflict becomes the job of the designer or the artist or the programmer who introduced the change. But we also thought, wouldn't it be nice if instead of having conflicts we need to resolve, if we had a way to prevent them from happening in the first place? And so the example where this blueprint class is being edited in 2 different streams, the fact that a user checks out the asset in one stream will send a message to a database, and then that database is looked up when you check out that file on another stream or that asset on another stream. And so in this case, instead of both people being able to check out the asset in different streams, the guy in the second stream gets a notification saying, hey, this user in another stream has this asset checked out. And then instead of making a conflict, the guy will get up from his desk and go and talk to the other guy instead. And if you want to add this facility to your version of the editor, you just need to add this little bit of code here. In this example here, it's manually adding each of the streams that it wants to add, is adding those in a hard-coded fashion. But for what we do for Fortnite is we just go off and read the RoboMerge configuration file. And that way, whenever we create a new branch, every time we've got a new release coming up, we update the RoboMerge configuration file, and then everything else continues on from there. So I've talked a lot here about resolving and avoiding conflicts when editing asset files. And something I know a lot of developers, including a lot of Korean developers, have been asking for a very long time is the ability to have text-based assets instead of binary assets for Unreal Engine. This is a fairly, as you can imagine, it's a fairly difficult thing to retrofit into Unreal Engine because we have a lot of serialization code everywhere. But our solution has been to implement something called F-structured archive. And this is just an extension of the existing archive class that we have, that we use for serialization. But as well as serializing the data, it has the annotations and the naming and the structure that goes along with the data. And this class has 3 different backends. The first backend is the raw backend, which doesn't do anything with the extra data and just continues serialization as before. So this is the backwards compatible loading and saving path that lets us load existing content. The second backend we have is with structural annotations and exporting the data as text. And this is a text format of the assets. So it'll be names of the properties, the array indices, and some text representation of the data for each asset type. And finally, we have a third, or this class allowed us to have a third backend, which allows us to have binary data, but with all of the structural annotations. So we've kept the data as it is in an existing binary format, but we've got all the information about it, like the names of the properties. And this allows you to write some tools that analyze your content in some really interesting ways. So we're intending to use it for that. Now, the great thing about this design is that when you're running on a console or on a mobile device, you don't care about text assets. You just want the binary serialization to work as fast and reliably as possible. And so using that first backend, we can save out the assets. And by removing all of the code related to this, we can comment that code out or compile that code out and then load that binary asset without any runtime cost for either RAM or disks or file size on disk. I must say, unfortunately, we're not quite yet ready to share this with you guys, but it is under active development. And if you look in the Unreal Engine source code, you can see some parts of this going on. So we have a team working on this, but we don't yet have a date that we can promise it being available to you. But just because we've got a text-based asset, it doesn't mean it's going to be mergeable. For example, you can have a text representation of a texture that is, a bunch of color value numbers. If you've got 2 of these and you have to merge them together, it doesn't really help. So anything with bulk data like a texture or an animation is going to have data that isn't really necessarily going to be easily mergeable. We also have a lot of data types in Unreal Engine that are based on nodes and graphs, like Material Editor or the Blueprint Editor. And these things are difficult because each of these nodes is an individual object which has this kind of 2D set of connections between them. And to export that into a text file is definitely possible, but it's difficult to understand that structure in kind of a sequential text file. And for example, a user could insert a new node between 2 nodes, and you would end up with a situation where a bunch of the contents of the file got renumbered because the node order changed. Or maybe you highlighted a bunch of material editor nodes and you move them slightly to the left, and you end up with a single line change in 20 or 30 places in the text file, recording that X coordinate that's changed for all of those entries. So it's not really a very useful, looking at a diff of this is not a useful information that you can't really merge these kind of things together. But still, we think the visibility into the asset types can still be valuable, and we have to start somewhere. It's possible we're going to improve our data structures to allow for better representations that might work better with text assets as well. The final section I'm going to talk about is how we iterate in Fortnite. And this is both content creators and artists, as well as programmers. So the first thing we do is we try to spend as much time in Play in Editor as possible. And so we think if we can get an artist to load up an editor session and spend the whole day there, iterating is definitely the preferable and most efficient way. There's a lot of, so when you're making an online game, there's a lot of things that Play in Editor doesn't do automatically for you that you probably want to get going. And so we've spent the time, and we recommend you spend the time to improve Play in Editor to make it work with your game login flow. So for Fortnite, Play in Editor allows you to connect to our live server or our development server and log in with your credentials or save your login credentials and enter a game in the multiplayer environment inside the editor. So you can test your brand new content in the correct environment or its final environment. We try to test using the full map where possible, so we don't test using test maps. We try to encourage our artists to work with the main content, and we try to design our game so it works well with Play in the Editor. And we've added extra tools to Play in Editor to allow you to launch multiple clients and a single dedicated server, so you can set up more complicated test situations that wouldn't come as default in the Play in Editor system. We also do use the editor binary with the -game and -server options to quickly run a game and a server in game mode without having to cook any assets. The soft references system that we have is a good way you can improve the editor startup time. But the first time a user loads up Play in Editor, the soft references will need to be loaded. So still, we do pay a lot of attention to how long it's taking to load up the Fortnite version of Unreal Editor and make sure our content has been designed in such a way that simply opening the editor isn't loading all of the game's content into memory, which is going to really slow down startup. So iterating for cooked builds, as you know, the cooker is one of the slowest parts of using Unreal Engine, and something we're working on improving. I'll tell you I'll give you some information about some of the lessons we've learned recently. First of all, creating the derived data or the cooked data is very slow, but it can be done in parallel. So if you set up a shared derived data cache, this allows all of your team members and your build infrastructure to be contributing the derived content in this central location. So if you don't know about the shared derived data cache, it's simply a shared folder that everybody can write to that we store the derived or generated platform data. We use XGE for compiling shaders. XGE is the automation tool part of Incredibuild. And shader compilation is one thing that is particularly slow for some platforms like mobile platforms that we try to get as much parallel benefit out of using multiple computers. And the rest of the cooker is usually CPU bound in the main thread. So this is just doing object serialization. Hopefully all the derived data is coming directly from the derived data cache. But the object serialization, loading objects into memory, is very heavy on the main thread. And for this reason, we found using computers with very fast cores, single core performance, with a smaller number of cores is much better than having a lower speed computer with more cores. So single core performance is what you should be optimizing for your cook machines for your build farm. We also have the ability to filter the packages that get cooked. There's that delegate there, so you can make gameplay decisions or higher level decisions about what assets you need to cook under which circumstances. And finally, when the cooker runs, it works by loading all the content into memory. And because some content references other content, you can get into situations where the same asset needs to be in memory for multiple times so that you can cook multiple different assets. However, the cooker has a memory limit, this max memory allowance that we've given the cooker, which defaults to 16 gigabytes. This is the maximum amount of memory the cooker will use before it runs a garbage collection. And so if your total system memory is larger than this, you'll get a much better, quite a big performance improvement during cooking if you increase that number. That will prevent objects being loaded and then loaded again later after they've been garbage collected. Iterating on devices, especially mobile devices, is rough. We're working on this. One thing we're working on is what we're calling shared cooked builds. And the idea here is that the build infrastructure will build and cook a build, and then if a user wants to test an asset, they'll be able to download the cooked build from the build infrastructure and just cook the single package or packages that they need, have those integrated together, and be able to deploy that to device. It's much quicker workflow. In our automation system, we have something called Gauntlet that was intended for automated testing, but it's actually quite powerful. It's capable of downloading multiple different builds, deploying them to a bunch of different devices, starting a server and having them join, collecting data and reporting that data back. And so we do a lot of our performance testing and performance reporting for Fortnite using automated systems like this so that we don't actually need to iterate on device to test the performance. This hasn't been documented very well, but last week we added documentation for Gauntlet, initial documentation, and there'll be more documentation for it coming with 423. But I definitely recommend looking into that. It's a very powerful tool we use for Fortnite. So if you want to iterate on some game code, for a long time we had this thing called hot reload, which what would happen is you would modify some code in the editor, in Visual Studio, and you would compile it, and that would make a new DLL, which would get loaded into the existing process, and then all of the object pointers would move from the old code to the new code, the new DLL. And provided that Unreal Engine captured all of the state, if it captured, if the object serialization system captured all of the state of your game, this would work fine. But in most cases, that's not realistic because often you have global variables and global singletons pointing to other systems that are not directly part of Unreal. And that made hot reload difficult to actually use in large-scale projects. So since, I believe, 421 or maybe 422, we've added, it's 422, there we go. We've added something called live coding, which is, it started off as a commercial product called Live++ that we've licensed and made available to you guys. It works in a completely different way to hot reload. Instead of uploading a new DLL, it simply patches the modified code directly into the running process. So only the functions you've changed will be updated, and so the global state and static variables, singletons, etc., will be preserved. One thing it doesn't handle very well right now is layouts to classes. So if you add or remove properties, live coding doesn't deal with that very well. We're working on improving that, so stay tuned. And finally, iterating in production. So we have a design requirement for Fortnite that any asset we create, any gameplay feature we add, any setting is able to be tweaked or disabled in the live build. And this gives us the ability to react very quickly to things we didn't find in our testing, bugs with new features, exploits in the wild with this particular weapon or a particular vehicle, any kind of glitches that need to be addressed really quickly because they're destroying the game. We can quickly address those using our online hotfix manager and make those changes extremely quickly, and then we can make a new client build or update the game code, etc., to solve these problems correctly. But it gives us the ability to react very quickly in a live environment, and it's been extremely important for a game like Fortnite where we're iterating so quickly. We don't have a super long time for very long QA cycles, etc. So the online hotfix manager is able to modify properties, is able to set control variables, and it can make global config changes as well. Anyway, that's a set of very random areas about how the tools we've developed for Fortnite and how we've made use of them in development. I'd be happy to answer any Q&A about anything I've said or anything else about how we work for Fortnite. Thanks very much.